Welcome to Hired in IT. Our mission is simple: help you build the skills that employers actually want. Whether you're trying to land your first IT job, switch careers, earn a promotion, or increase your salary, we're here to help. Every video is thoroughly researched and designed to make complex IT topics easy to understand. If there's an IT topic you'd like us to cover, leave a comment below. We may turn your suggestion into our next video. Turning IT knowledge into career opportunities. Last time we cracked open a computer and mapped the guts. Now we're zooming into the chip that calls the shots, the Central Processing Unit or CPU, the brains of the computer. It's noon at a national bank. The online trading portal freezes. Trades don't execute, transfers fail. The network team runs every diagnostic, everything checks out. The real bottleneck? The server's CPU struggling to keep up because its processing capacity was maxed out, causing transactions to pile up and costing the bank tens of thousands in lost deals in a single hour. This is why understanding what a CPU actually does isn't just a spec sheet detail. It's how you stop an invisible meltdown before it starts. By the time this video ends, you'll have 3 concrete skills. First, you'll understand the fetch, decode, execute cycle that powers every processor. Second, you'll glance at a spec sheet and instantly know what Core i7-13700K tells you. And third, you'll match any workload to the right CPU using real-world benchmarks like Passmark and Cinebench. A CPU is the component that executes instructions. Every app, every click, every keystroke. Think of it as a world-class chef. Incredibly versatile, can whip up a 5-course meal or a delicate soufflé, but only 1 or 2 dishes at a time. That's the CPU's superpower and its limit. Modern CPUs run at gigahertz speeds. That's billions of clock cycles per second. But they still process instructions one tiny step at a time, just like the earliest computers. Every CPU runs an endless loop called the instruction cycle. First, fetch. The CPU grabs the next instruction from RAM. Then decode. It cracks that instruction into tiny micro-operations it can actually swallow. Finally, execute. The arithmetic logic unit does the math, like grabbing the values 100 and 200 from memory and adding them to get 300. That's fetch, decode, execute, often just called the FDE cycle. Zoom inside and you'll find 3 key units. Everything inside the CPU moves to a beat, a clock signal that pulses billions of times a second. Each pulse, or clock cycle, is the smallest unit of time for the CPU. The control unit is the conductor. It decodes instructions and tells the rest what to do. The arithmetic logic unit does the heavy lifting, addition, subtraction, logic like AND and OR. Registers are the CPU's own scratchpad, holding data so close it's accessible in a single tick of the internal clock, 1 clock cycle. For a simple AND operation, the CU loads the 2 values into registers, the ALU crunches the logic, and the result lands back in a register. Quick checkpoint. Name the 3 stages of the instruction cycle, and which unit jumps into action during the execute step. Early processors ran at just a few megahertz. Modern chips push into gigahertz territory. But raw clock speed isn't the full story. Instructions per clock, how much work each cycle does, has improved dramatically. A chip from a few years ago at 4 GHz can be outpaced by a current chip at 3.5 GHz. Because the newer architecture does far more per cycle. That's why architecture often matters more than pure frequency. Let's define a core. Each CPU core is an independent processing unit, like a separate chef in a kitchen. A single chef can cook one dish at a time. More chefs can cook multiple dishes simultaneously. That's why more cores help with multitasking. Each core handles its own thread of instructions, so your system can run multiple apps in parallel without slowing down. To avoid waiting on slow RAM, every CPU has a pyramid of cache. L1 is tiny but screaming fast. Data arrives in just a few cycles. L2 is larger, private to each core, and still fast. L3 is a big common pool all cores share, but a miss there means a trip to system RAM, often costing tens of cycles. That's why cache size and design directly boost real-world performance. Let's lock this in. You've learned about cache. Now, a quick recall. What is the main reason a CPU includes cache memory? Every CPU speaks a specific language, its instruction set. x86, used by Intel and AMD, is the complex, feature-rich language of desktops and servers. ARM is the simpler, power-efficient language that dominates phones and, thanks to designs like Apple's M series, also powers many laptops and tablets. ARM-based chips like the M2 deliver all-day battery life in thin laptops, while high-end Intel desktop chips push high FPS gaming but draw much more power. Different languages, different strengths. 3 companies design the CPUs that matter to IT pros right now. Intel still leads total volume with its Core series and strong single-thread performance. AMD has been eating into that lead with Ryzen chips that give you more cores for your dollar, and Apple's M-series chips are efficiency monsters. They pack billions of transistors, the microscopic on-off switches that power the chip's logic, delivering remarkable performance per watt. AMD and Apple don't even own factories. They're fabless, relying on TSMC's cutting-edge manufacturing. Intel and AMD model names look like alphabet soup, but they follow recognizable patterns. Let's decode a Core i7-13700K. The first numbers, 13, suggest it's from Intel's 13th generation, but always confirm on Intel Arc. Suffixes like K often indicate an unlocked multiplier for overclocking. Check the spec sheet. An F typically means no integrated graphics. AMD's Ryzen 5 7600X, the 7, suggests 7000 series, and X often means a higher clocked version. Verify on AMD's site. Decode the SKU, and you instantly know what you're getting. Clock speed is a spec, but benchmarks tell the truth. Instead of chasing gigahertz, use tools like Cinebench R23 for real-world rendering, Passmark for a broad system score, and Geekbench for cross-platform comparisons. Numbers vary wildly based on architecture and core count. A modern budget chip can outperform a many-core processor from a few generations ago. When buying cross-check Passmark and Geekbench scores, not just the box label. A budget builder scores a cheap many-core Xeon on eBay, thinking more cores equals a faster PC. But in Photoshop, the timeline stutters, brushes lag. Single-thread performance is far worse than a modern entry-level chip. They just wasted a couple $100 because they ignored the spec that controls how well each individual core performs. If the chip can't stay cool and fed with enough power, all those cores are useless. This is a mistake you will not make now. Thermal Design Power, or TDP, tells you how much heat a CPU produces at its base clock. A Core i9 might have a base TDP of 125 watts, but under turbo boost, it can spike much higher, sometimes 50% above base. Check the maximum turbo power on Intel Arc or AMD product pages for your chip. If your cooler only matches the base TDP, the CPU will thermal throttle under heavy load, cutting performance to avoid damage. Always plan for the peak, not just the base. Overclocking means running a CPU faster than its factory settings to gain additional performance. By increasing the processor's operating frequency, some workloads such as gaming, video rendering, and simulations may complete faster. However, higher performance also means higher temperatures, greater power consumption, and potentially reduced system stability if the settings are too aggressive. Successful overclocking requires a compatible CPU and motherboard, a high-quality cooling solution, and careful testing to ensure the system remains stable under heavy workloads. While modern processors already boost themselves automatically, manual overclocking remains an option for enthusiasts who understand the trade-offs between performance, heat, power, and reliability. Let's check your overclocking knowledge now. CPUs physically mate with a socket on the motherboard. Intel's recent desktop CPUs use sockets like LGA 1700, while AMD Ryzen 7000 series uses AM5. The pads on the CPU have to match the socket's pins exactly. A mismatched socket means the CPU won't even sit flat, let alone boot. Always verify socket compatibility for your exact CPU and motherboard before you hit buy. Quick checkpoint on CPU sockets. At first glance, CPU prices seem insane. A tiny piece of silicon for $600. But looking back, it's a bargain. The first microprocessor, the Intel 4004, contained 2,300 transistors. Today's chip holds billions. If transistor count scaled linearly, that modern chip would cost millions. But it doesn't. The real cost isn't raw silicon. It's the decade of R&D, the billion-dollar fabrication plants, and yield, the percentage of working dies. Each tiny square cut from the wafer is called a die, the actual processor chip. A single dust particle can ruin a chip, so yields for new processes can start much lower than you'd think. You're paying for the risk, the yield, and the insane engineering. Making a CPU is closer to printing a city map with light than assembling a machine. It starts with a pure silicon wafer. Photolithography projects the chip's design onto the wafer using ultraviolet light through a mask. Then etching carves out the unwanted material, leaving behind the transistor shapes. Doping introduces impurities to create the electrical properties that form transistors. Layering builds up the interconnects and metal layers on top. Finally, the wafer is sliced, tested, and the good dies are packaged into the CPU you hold. Today's most advanced processes can pack an astonishing number of transistors into a single square millimeter. A single microscopic defect at any of these steps can kill that entire chip. Let's check your understanding of why silicon isn't priced by the transistor. Picking the right CPU isn't about buying the most expensive one. It's about matching specs to your needs. Consider socket compatibility, memory support, power requirements, and real-world benchmarks. Use a site like PC Part Picker to verify compatibility before you buy. Before we move on, let's test what you just learned. You're building a gaming PC and spot a great deal on an i7-13700K. Is a B-series motherboard a good match? Pause and think. No, it's not. B-series boards usually lock CPU overclocking, so you'd lose the K's multiplier advantage and pay extra for nothing. If you got that, you're avoiding one of the biggest builder traps. That's a wrap on CPU fundamentals. You can now explain how a processor actually works, interpret core counts and clock speeds without getting scammed, and walk into a store knowing exactly which chip fits your job and budget. The engine is yours. Next stop, RAM. Hit subscribe so you catch part 3 and tell me in the comments. What was the first CPU you ever upgraded? See you there. Remember, careers aren't built by watching videos. They're built by applying what you learn. Pick one thing from today's lesson, build it, document it, and share it. That's how you get hired. Thanks for watching Hired in IT, where we're turning IT knowledge into career opportunities.